Yeah, amplifier design. So we'll first discuss the common source amplifier. I know from the introduction to electronics you are already aware of this topic, but we'll little bit see from the VLSI perspective. So in VLSI, basically we have to, depending upon the situation, some things we need to keep the focus, right? So for example, when we are dealing with the discrete components, right, which we do in introduction to electronics, we don't care much about the body bias or even RO. We don't care much. Like, yeah, we assume that, but what happens? It becomes very significant when it comes to the VLSI implementation. Right. So first question is, why do we basically need an amplifier? So amplifier is required everywhere. For example, we have this kind of RF communication, right? Whether it may be, transmitter or receiver. So I have this antenna. So I have my receiver here. So a receiver here, I have this LNA. LNA stands for the low noise amplifier, right? And I have this power amplifier at the transmitter end. So power amplifier, because I need to, whenever I am transmitting, because I am transmitting to far maybe distance, right? Maybe from my mobile phone to the cell tower. So I need to boost the power of the signal so that it can sufficiently reach the tower, right, from my mobile phone. That's why I need a power amplifier. So here my main focus is getting the power as high as possible, right? The other thing is, when I'm receiving it, you can see here, I need a different kind of amplifier. Although it's an amplifier design, but the characteristics are different and the requirements are also different. So here, if you see, if I'm receiving the signal, I have a low noise amplifier. So low noise amplifier, what it means is, the amplifier itself will have some noise. That also maybe we'll learn eventually, that when we are designing an amplifier MOSFET, it also basically generates some noise. But that noise is like really in very small order, maybe millivolt or microvolt. But still, since we are receiving the very weak signal, like if the tower is far, we are receiving the signal, that signals are quite weak. So that's why I want to make sure that whatever the amplifier that I am designing should not add noise to the signal. That's why it should just amplify the signal and it should not add noise. So that's why they are called low noise amplifier. Of course, it cannot deal with the noise that is there in the signal. What it means is that this amplifier itself should not add noise when I am amplifying the signal. But whereas the power amplifier requirement is little different, so I just need to make sure that the signal, whatever I'm trying to transmit, should have a high power enough at this node. So now the challenges is, because we are going for a wide swing here, right? So linearity matters a lot whenever we are designing this kind of power amplifier. We want the amplifier to be operating in a linear region. So we know that amplifier, the expression is yt equal to alpha 1 xt. So xt is my input, alpha 1 is the the amplification. So we wanted this to be linear, especially it is in this power amplifier, it becomes important. So what do we mean by the linearity? Linearity, ideally I should have yt equal to alpha 1 xt, right? So it should be a straight curve. Of course, there may be an offset which is alpha naught, maybe DC offset we can consider, but whatever it may be, this slope should be quite constant. But this is ideal case. But in actual implementation, when we are designing the amplifier with the transistor, it will not have that kind of this curve. We may have this kind of curve. There may be the area may be smooth only in this area, and it may also not be perfectly smooth, right? I mean, it may not be perfectly linear also. There may be some non-linearity component. So actually we can model this kind of non-linearity using this kind of expression, right? So instead of just 1 alpha 1 xt, basically and this alpha naught, so this is the DC component, DC value. So I will have some other terms, alpha 2 x square t, alpha n x n t, right? So x power n t. So it will have many orders. Of course, this depending upon like this may be small values like that. So but we can see that there will be these terms like if I want to model these characteristics perfectly mathematically, what happens is when I think if you have read in the signals and systems, so when we try to square the signal, of course this alpha 2 may be very small compared to this alpha 1 may be dominating, but what happens if I square a signal, if I have a frequency at omega, if I square and take higher orders, I can have signals at 2 omega, some component at 3 omega, right, the harmonics basically. And what will happen is, especially if I have multiple kind of, I have this desired signal, this interferer signal, and if it is not properly dealt, there can be like this, this can overlap with the desired signal because of this kind of non-linearity. So especially in case of the power amplifier design, because we are amplifying it, right, our magnitude will be very high. That's why taking care of the linearity aspect in power amplifier becomes trouble. So now the next thing is what are the different parameters of an amplifier design. So yeah, as I mentioned that power amplifier, the linearity becomes a factor, noise is also an important factor, power dissipation. So these are the different parameters that a designer try to focus on and try to optimize it, right? And so input and output impedance, right? Especially the RF, transceiver should have 50 ohm input and output impedance. So those things. The next is the speed, right? I should also have good bandwidth. Otherwise, if you have to operate at high gigahertz range and all, speed is also important. Voltage swings are important. Voltage swings and maybe the linearity has a dependence, right? So and then of course the supply voltage nowadays, people are going for even lesser than 1 volt supply. So in that situation, how do we take care of the gain of the amplifiers and all those things? And finally the gain, right? So all these are some of the important parameters which are dependent on each other basically. So if I try to maybe improve the noise performance, then it may affect the power dissipation or it may affect the linearity. So how do we optimize the design? So that is the main role of an analog designer. So how do we get the specification? How do we get a particular linearity? And what are the things I should compromise on, like that? So those things are there. So we have basically, it can be divided into 3 types of amplifier. One is the common source, common drain, and common gate. So this is my common source amplifier. We call it a common source because the source of the MOSFET is common to the input. It is grounded basically. So it is common to both the input and it is common to the output. So that's why it is called a common source amplifier. Now, if we try to see the input output characteristics, so this curve is called the input output characteristics. So if I slowly try to increase the input voltage, let's consider only the DC here. So we are just applying a DC voltage here. And we are slowly increasing this potential, and we are trying to see how does the output varies. So when the voltage is really small, right, this transistor is in cutoff state. So there is no current flowing through this RD, and this V out is equal to VDD. Now slowly if I increase this voltage and such that this V in is equal to VTH, the threshold voltage, then this MOSFET starts conducting and some current ID starts flowing through it, right? Just like maybe very small. Now if I increase this voltage further, then this current starts flowing and there will be a drop, right? VDD minus IRD drop will be here, and this V out slowly starts decreasing. So you can see here it will decrease. So and at one point of time, so of course now it is in saturation region. From cutoff region it has gone to the saturation region, and then it will slowly, as this goes down, it will go to the linear region. Yes. So basically whenever it goes and so whenever this voltage exits this one by VTH, right, then we know that this will go into linear. So this is shown by this diagram, this node here. So this voltage is higher than this drain, the gate is higher than drain, by VTH. So yeah, so as we had mentioned in the last class, so we just need to look these two node voltages, and if this node voltage is higher than this node voltage by VTH, we know that the transistor has started going into the linear region. Now if we observe the V in versus V out characteristics, we know that this region, this region, although this region is very small, this region can be used as an amplifier, right? So whenever it is in the saturation region, this region can be used as an amplifier. We don't generally use the linear region. It's not very, it will add a lot of harmonics. So this region can be used as an, for designing the amplifier, right? The linear region can be, I mean the linear in the sense that this straight region can be used as an amplifier design. So now the next point is, how do I know that how much gain is this? So how much gain is this? So that we can see that that is very simple. So if I just write down the expression of the V out in terms of this current flowing through this ID. So the V out is nothing but, we know that V out is nothing but VDD minus IDR, right? So an ID in saturation region, because we want to deal with this saturation region only. So VDD minus RD half mu n Cox WL Pn minus VTH whole square. Here at this point of time we are neglecting the 1 plus lambda VDS, the arrow. Now if we want to know the gain is basically, the gain is like if I have a small change in the I just want to find out the slope basically. If I have some change in the input, how it is getting reflected at the output. So basically it is slope, right? So that's the gain, right? So the gain is, if I differentiate this expression, if I differentiate it, then what I will get is minus RD mu n Cox WL Vin minus VTH. Now if you see here, this expression is nothing but the expression for the GM, right? Which we had discussed in the last discussion. So this expression is GM, so the gain is minus GMRD. So this is one way of seeing this, the common source amplifier. There are different ways to come to this expression, but this is one of the ways by which you can come to this expression of the minus GMRD. Now we can definitely write the expression of the GM. So last time we have seen that GM has different expression. So if I try to use this expression, right, 2 mu n Cox WL ID. So this is also one of the expression of the GM, right? And RD I can write in terms of the voltage drop and the ID, right? So we know that the voltage drop across this D is ID into RD. So RD is nothing but VD into ID. So we can write like this, right? Correct? So I can write this RD something like this, right? So this is my RD, which is VRD. Sorry, I had written VD, but it is VRD. So potential across RD into ID, and this is the expression for the GM. This is the expression for the GM, and this is the expression for the RD. Okay. Now, of course, I can cancel out this ID and ID. It is square root ID and this ID. So finally, what I'll get here is VRD by ID. So now this leads to a very some conclusion you can get from this expression. Now, if I want to increase the gain, what are the parameters I have? One thing is I can increase W by L ratio, which is generally done like that. And the other thing is I can increase the voltage drop across this one, or surprisingly you can see that if I decrease my ID, right, then it is possible. But of course, if I am decreasing the ID, VRD is also increasing, right? So I need to increase RD if I am decreasing ID, because I need to keep this constant, right? basically if I am keeping this, if I have to keep this constant, and if I am decreasing RD to increase the gain, then I have to increase my RD, right? So now what are the consequences of all these things? Like what are the consequences of these things? The consequence is if I try to increase the W by L ratio, right? W by L ratio, note that it will have a capacitance CGS, right? CGS, the capacitance because of this W and L. So this will be loading the previous stage, right? This will be loading the previous stage. Moreover, there also will be CZD also will be coming into this picture, and it will reduce the bandwidth. So bandwidth will get reduced when I'm trying to increase the gain by increasing W by L. So that's the trade-off, right? So this let's see these three parameters basically. Of course, we have many parameters, but out of which if I just consider this three, so that's the trade-off. Then we need to see that how we are taking care of this trade-off. So these are these two things. Now, so we cannot arbitrarily increase W by L. So in fact, the reason for only going for very low technology, this is also one of the reason where in the fabrication we are trying to make this L as small as possible. Like people are going for 16 nanometer, 5 nanometer. Of course, in the digital it helps a lot, but in analog also, in one sense, it is helping because it is improving the W by L ratio, right? Right, W by L ratio. So gain is getting higher, but it has some other issue also going for lower technology. Of course, the gain is not, even though we are going for good higher technology, 65 nanometer, 28 nanometer, the gain is reducing basically because of some other reason which we will discuss little later, right? Not because of this one. So now the other thing is if I try to decrease this ID, so I need to keep this constant, so I need to increase my RD, right? If I am decreasing this current, I need to increase the RD, right? And so that my so that my this remains constant. But if I increase this RD, definitely it will also be driving some capacitance. So the RC time constant or the bandwidth will get affected. So bandwidth will decrease. Of course, there is also the power. I should have written the power also. If I decrease the ID, the power will. There is one more parameter, power. So power will get reduced, but the bandwidth also will get reduced basically. So this is also one trade-off. Now, what about if I increase this VRD, right? What happens if I increase this VRD? So if I increase this VRD, what will happen is my swing will get limited, because if I increase this VRD, it can push this transistor to the linear region. So the swing will get affected. So if I am trying to increase the gain by increasing this VRD, my voltage swing will get reduced. So this is again trade-off. Of course, because my VDD is constant, so I cannot increase my VDD. So in a chip, in an IC, we have only the VDD fixed, maybe 1 volt or 1.2 volt, something like that. Okay. So so the point here, the takeaway point here is that when we are designing a transistor, it is not just if we want to increase the gain, it will increase. So there is a trade-off, and we have to find out the optimum point. The next is okay, we'll do some small signal analysis, right? So if we are dealing with MOSFET, so just if you are having a MOSFET, as we have mentioned last time, we have this ZM VGS. We just need to make the VGS plus and minus here, and right, and then we have this drain, and we have this gate, and we have this source, right? So we just need to use this model and put it here. So, and of course we have this RD here, right? So RD will be coming here. So RD. So in the book, I have taken this diagram from the book. So instead of VGS, it has used this V1. So it is the ZM V1 here. It's the current conductance and the RD. So this is a clear picture. So let me delete this one. I think this is clear. So we have this GMV1. So this is my MOSFET. So where this is my gate, this is my source, and this is my drain. So when you are given any circuit to do analysis, try to break down like this. and it will be very easy to do the analysis. So what we have now here is the current flowing through this is, suppose this is, let it be I out, right? So if I write this I out, so I out is nothing but here this GMV1. And what is I out? I can write this I out in terms of RD and V out, right? So because this current I out is flowing like this, so I can write this as what I can, so equal to GM V1, right? And V1 is equal to V in, so I can write as V1 is equal to V. So what I have here is V out by V in is equal to minus GMRD, which is also nothing but the gain, right? So it's the same thing, like same thing whatever we have derived like that. So we can do the same derivation even from the small signal analysis. So now let's make it a little more complicated. I think you already had done this kind of analysis before, but let's move to some little more. Let's try to add some more non-idealities. So let's try to. Is my voice audible?
Yes.
Okay. So if I put the arrow, so we have not put arrow here, right? We are supposed to put the RO due to the this one due to the this factor, right? Due to the this RO that is coming from the channel line modulation. So if we put the RO, so how does the gain expression change? So the gain expression change, I have put an arrow here, right? So this arrow is coming parallel to RD, right? So arrow is coming parallel to RD, so the gain expression will be nothing but just minus GM arrow parallel RD, right? So of course, if I want to find the output impedance of this node, input impedance is infinite, that is very sure. Input impedance, if you see here, it is infinite because it's a MOSFET. But output impedance, so if I want to find the output impedance, the procedure is I should ground the I mean I should short this the V in, or I should put it to ground, right? So if this put is ground, that means this is this will not be there, this will be 0. So the output impedance in this case is RD parallel RO. So R out is RO parallel RD. So these are quite simple analysis. You also have done it like that. So now I have one question. So the next question is, what is the maximum gain that I can get from this amplifier? What is the maximum gain? So we cannot go beyond that. Basically, that's the limit. Are you getting my point? Or what is the maximum gain if RD goes to infinity, right? Suppose assume that I have an option to go take this RD to infinity, right? So the maximum gain possible is only minus GMRO, right? So this is the maximum gain that is possible, right? We cannot go beyond this point. So now in this current technology, when we are discussing about 65 nanometer 4 to 10. So this intrinsic gain is only 4 to 10, right? So so it is not. It is like, it is very scary, you know. You generally, if we are designing with a BJT, right? If you have in introduction to electronics lab, you must have seen getting a gain of 100 or 200 is so simple. But in the current technology, because this RO is so bad, because of the lambda being so bad, right? This RO is like this, it has this kind of characteristics. That's why that's a challenge of designing a very high amplifier in the latest technology. So the following, hello, yeah.
Yes.
Okay, great. But now the question again arises: how do you get this RD infinite, right? How do you get ideally, like how does it looks like the circuit? So the circuit looks like something like this. if I put a current, ideal current source here, right, flowing a current ID, right, right. So in this case, the gain expression is GMRO. So this is the circuit which will give you, like, if I use an ideal current source and if I just do the simulation, so this will give me the maximum gain that is possible, right? So if I have some RD, ideally it is not possible to get an RD infinite, because ultimately we will also be implementing this current source with MOSFETs only. So ultimately it will be lesser than GMRO. So this is basically the maximum, the ceiling basically. Okay.
So, but that's not practically possible. So, how we will
Okay.
implement that means the perfect current source?
Okay. How do we implement a perfect current source? Yes. So the answer is, of course, like, it is not possible to get the perfect current source. So, and in fact, even if you are implementing with a perfect current source, you see my gain is still 4 to 10, right? Even if you are implementing with a perfect current source, the gain is still 4 to 10. But if I need a gain of 50 or 100, even if I am implementing a perfect current source, it is not possible. So I need to go for different architecture or different topology. The conclusion here is that simple common source amplifier cannot give me a high gain when I am dealing with a technology which has a very bad RO, right? Very small RO. So that's the conclusion, right? So, following? Yeah.
Yes, sir.
Yeah, yeah. That's good, good. Yeah. So the next is so now we'll be discussing. Okay, what should we do in this other technology? How to get the better gain? So that's the other topic that we will be discussing eventually. So now the next modification what we'll do is, actually this will give the answer. This will give the answer to our question, that how do we increase the impedance. This circuit will give our the solution for this. So now if we have this source degeneration, how does the gain affects? So again we'll be writing the MOSFET here. This is my MOSFET which is a gain. Let's call this voltage Vs. What is V1? I mean this voltage V1.
Vn minus Vs.
Vn minus Vs. Okay. So now I can write, what I can do is, I can write this Vs in terms of I out and Rs, right? Agreed? So I can write Vs in terms of, so I can write Gm. Vs is nothing but the same current is flowing through Rs. So I have I out Rs, right? Clear? So I can I can bring this I out this side. I want to bring this I out this side and equate it. So 1 plus GMRS is equal to GMV in. And via I out I can write it as what I out I can write it as minus V out by RD again, V out by RD. And I can take this side. So in the denominator, GMV in by 1 plus GMRS. So now if I just reorder it, like if I bring this Vn and take this RD this side, what I'll get is I'll get the gain expression something like this. So minus GMRD plus 1 plus GMRS, right? So this is the basic expression of source degenerated common source amplifier. So the next question is, what happens if my GMRS is large? What happens? If my GM is big, what happens to this expression?
Gain will be low.
No, if I increase the GM,
It will be Vn by Rs.
sorry? if I'm increasing this GMRS and make it very large, so this will be much greater than 1. So I can approximate it to RD by RS minus RD by RS. Okay, so this expression is interesting. So in a common source with source generation, if I have RS and RD, so the point here is if my GM is large, my gain is not at all dependent on GM. So this is an important conclusion here. So these circuits are especially important whenever I want to make my circuit very linear. So this is because this resistor is a linear device, GM is a non-linear device, right? So this circuit is specially used when I want a very high linearity, because my gain, if my GMRD is much larger than RS, much larger than 1, my gain is just dependent on RD and RS, which is, and both this RD and RS are two resistors and both are linear devices. You getting my point? So, and because of which we can get a very good linearity. Following this point? Hello? Are you able to follow this point? Appreciate this point?
Yes. Yes, sir.
Yeah. So this is one technique which is quite frequently used to get a very linear kind of amplifier. Of course, with other modification, but this is the basic concept how it starts. So now the next point is okay. So now I have just analyzed it. So next will be little interesting. The analysis is complicated, but this is quite interesting, and you can try at home also, like that. Try to do the analysis. So what will be this expression if I include RO and the body bias effect also, GMB, right? In the small signal model of the MOSFET, if I include the RO and the body bias effect, how does it happen? So if I include the RO and the body bias effect, this will be my complete model of the transistor, right? As we have discussed before, I'll have this RO, I'll have this GMBBS, right, and GMV1. Other it will remain same. This is my source, this is my gate, and this is my drain. Okay. So now if I just write the expression of again, this is my drain. So if I just write the expression of the I out here, again let's start the same kind of analysis. It's again the same way we do. So if I just write the I out, it will be again, what are this? Can you help me? What will be my I out, total I out in these three terms? Yes.
GMV1 plus GMVBBS plus V1 by R naught.
Plus, yeah, so the current flowing through is V out. No, this voltage is now different, right? It's not ground, right? So it will be V out minus Vs, right? The potential difference across this RO is V out minus this small Vs by RO. So now what will be my V1? So what will be my V1? Again same thing, Vin minus Vs. What will be VVS? What will be BVS? BVS is V bulk minus Vs, right? So what is B bulk? What is BBS? Yes. It is a ground, right? Bulk we have connected to the ground, right? So bulk terminal will be always connected to the ground, right? So this is 0. So BVS is 0 minus Vs. And what I have here is V out minus Vs by RO, right? So now if I just multiply it, right, and if I just multiply it and make some rearrangement, so I can multiply this RO with everyone, and VS is nothing but, again, VS is nothing but this, if I write in terms of I out, it's I out into RS, right? Just like we have done before, GM V in minus this is I out into RS, and again this is plus GMB I out into RS plus V out minus V, again VS is by RO. Okay. So of course this one. So now if I just rearrange it, if I multiply this one RO here, here, what I will get is I'll get this kind of expression. Let's use black pen here. So what I'll get is I out RO is equal to GMB in RO minus GM I out RS RO plus, so again, sorry, this is GMB, and it will be minus here. So minus GMB I out RS RO plus V out minus I out into RS. So now if I put I out as again V out by R minus V out by RD, if I replace this one, what I will get is V out by V in, the gain finally. I'll have a little big expression, something like GM RO into RD by RO plus RS plus RD plus GM plus GMB into RS RO. So you can try yourself to solve this, maybe to get this value. It's a good exercise, right? So this is the gain. So if I make this RO infinite, again I'll get to the same expression whatever I had get here, right? If I divide RO with everywhere, and then so this will be 1, this will be 0, 0, and again this will be GM plus GMB into RS. Now note that you see the GMB gets added to GM. So we'll see this kind of expression in most of the time, that the GM gets added to GMB, right? So this kind of expression we'll get. Okay. So I think you can try out to derive this point. Definitely I'll just correct the notes. Yeah. Yes.
So this bulk voltage has come because VS is no more grounded, right?
Correct. Yes. Yes. VS is no more grounded. That's why we have because the bulk is grounded, but because of some current is flowing through it. So because this potential has changing, right, with the signal. So that's why this VVS is coming into picture. Very correct. Absolutely correct. And it is affecting the gain. You can see that this factor is coming into picture. So it is reducing the gain basically in one sense. Okay? Yeah.
Yes.
Yes. Yes. So yeah. So that's it. So the next important, I should say this is the most important. This will be easier to follow, and this conclusion will be better. So what is the output impedance of this? What is the output impedance of this circuit? What is the output impedance, right? If I look into this one, what is my output impedance? To see the output impedance, I can break this resistance and this part, these two parts apart, so that I can individually analyze it. So if I break this two part, right, just for my sake, understanding sake, if I am breaking it, so this is basically the impedance looking it into this is RD, and the impedance looking into this is, maybe let's call it as RX, right? And then what will be my R out? Total impedance R out looking into this will be RD parallel RX, right? So now my main goal will be to find out the impedance Rx. Okay, so if I want to find out this impedance Rx, right? So I can do a simple calculation. Again comes, if I see this Ix, my Ix will be nothing but, again, same kind of analysis. Again we are repeating it, GMV1 plus again Vx minus Vs, if I call this as Vs by Rho, plus again this GMV VVS, right? So now yeah, so now if I okay, so if I just rearrange it again, right? So again this Ix will be Gm by V1 is nothing but, again now it will be minus Vs because Vin is 0, so it is just minus Vs, right, plus Vx, yeah, Vx is again minus, it's plus Gm, again this is also my Vv is 0, so minus Vs, okay, same thing. So now let's multiply with Rho everywhere. So Rho, so this is Ix, Rho is equal to minus GMVS and plus Vx minus this Vs I can write, actually this Vs I can write in terms, let's write it later maybe, plus minus again GMV Vs, right? So Vs I can write it as Ix into Rs, right? This is Ix into Rs. So if I write like this, minus Gm Ix into Rs plus Vx minus Ix into Rs minus GMB Ix into Rs. Okay. So if I just again the same figure I have mentioned here. So if I just continue and if I just take Ix common here and bring all these terms with Ix, what I'll have is have Rho plus Rs plus Gm Rs plus GMB Rs equal to Vx, right? So therefore my Rx, the impedance looking into this point Rx is nothing but, which is Vx by Ix, right? Vx by Ix, because I need to put a voltage source here to find out the output impedance. I hope you know this. So if I want to put an output impedance, we have to put a voltage source here, ground the input and put a voltage source here. So this is the procedure for finding out the output impedance. So Rho plus Rs plus Gm plus GMB, so the GMB part always here, into Rho Rs should be there. Actually this is yeah, I missed the Rho here, and there also multiplication of Rho will be there everywhere. This Rho. Okay, so this expression is very important and we should remember this. Looks like little complicated, but it's not tough. It's not complicated to remember. I have put a summary at the end. So what it means is, if I have this kind of configuration, the impedance looking in this point is Rho plus Rs plus Gm plus GMB into Rho Rs. So this is a very significant conclusion. Why? Because the impedance here is quite high. You see, I am having GM and RO into RS, right? If my this RS is large value, right? We'll see later on that in some cases that RO is same as this. The RS can be made same as RO if I am implementing a current source here. So basically, this is if suppose this RA is order of the same as RO, and suppose neglecting this GMB also, this can be order of GM RO square, right? GM RO square, because I can this term GM RO square is much larger than this RS and RO, so I can get a very high impedance which is equal to GM RO square, right? So if this RO is 4 kilo ohms, we can know that it will be like square of that. So it is possible to implement a very high, uh, a very high impedance using this kind of configuration. So this kind of configuration is frequently used to get high impedance in high technology like 65 nanometer. As we are going to less than 180 nanometer, when the RO is becoming very small, so we have to go for this kind of configuration to get high output impedance, because we know that the gain is very much dependent on the output impedance, right? Ultimately, the output impedance into GM is the gain, right? So if I am having an output impedance something like this, then it is possible to get very high gain basically amplifier. Any questions on this point? Any questions? Are you able to follow this one? Yeah.
So why RO square, sir?
What? Sorry, why RO square, right? So assuming that RS is like I am taking RS close to RO, right? Maybe if RS is equal to RO, if I can put this RS of the order RO, right? That's why it is RO square. Right? I will see that we'll see in the later stage in the implementation, it is possible to make RS equal to RO. What I want to emphasize on this point is that this impedance is very high because of the this kind of expression. Product is there, not two resistance. That's my point. Like that, it can be other. I have just it's not the general expression. It is RS into RO definitely. But just if suppose if my RS is equal to RO, if of this order, right? Then like that. Are you getting my point? Hello? Yeah.
Yes.
Yeah. So basically, what happens is in analog electronics, we have to do a lot of approximation depending upon what is the orders and all. That's the engineering, right? Sometimes we may not go for the absolute expression. What is because ultimately, suppose if my this is like suppose if my this RO is maybe 4K, right? And this RS is also 4K, and this is 4K, right? GM maybe like GM maybe let's consider the GM maybe. I know it's not possible to make maybe like 1 by 1K, right? Because it's a reverse of the impedance. So total what we'll have is or 0.5K, right? So then total how much we'll have is around how much is this value? 4K into 4K and by 0.5K, so it's approximately I should say that it's 32K, right?
GM is like 1 by 200, 1 by 400 types.
1 by 200, yeah, it's around 1 by 200 ohm, 1 by 200 something like that, yeah. Suppose if a 1 by 200 or like this is like that, so then it is of the order of maybe 40K something like that, right? So yeah. So what I mean here is that depending upon what is this value, right? So this term will dominate. So that's my only conclusion like that. Okay. So this kind of is the point. This point is clear, right? GM RORS. So this is like a very important because once we these are the different types of this is the only technique which is used to implement high impedance or like high gain op amp basically. If you are designing any op amp nowadays, like whether it may be analog device or they will use this technique to get a very high, if we are buying a analog electronics, this one from like TI or something like that. So they use this technique to get a very high output impedance op amp, like high gain op amp basically. Okay. Okay. So the next, I hope any questions in this? Yeah. So if you don't have any questions, so let's again maybe discuss again this point. Okay, the gain, we already have this gain bandwidth trade-off. So, and the point what I want to mention here is, it is not possible to increase the RD with this passive device. So the other way to implement RD is this way, going for a PMOS load, right? So going for a PMOS, not that this voltage is fixed and this voltage is fixed to such potential such that this both of them are in saturation region. So if I draw the small signal of this one, if I try to draw the small signal of this one, it is something like this. So if I try to draw the small signal of this one, so let's draw it black. RO1, so let's call it as ZM1 and RO1, and this is the V out. So similarly, this is the gate, this is the source, this is the drain, this is shorted at the ground. So I can draw similar kind of things for the same, for the PMOS device also. PMOS device also will have same kind of configuration. Only thing is that now my source is not sorted here. My gate is sorted to a, because it's a fixed DC voltage, right? In terms of AC analysis, we know that it should be grounded. I hope this is fine for all of you, the concept. And the source is connected to, okay, source is connected to VDD here. So again, this also will be AC wise, it will be grounded because there is no AC signal, right? So there is no AC signal, here. It's fixed potential, and the drain will be definitely connected here, right? It will be connected here. Right? So this is the small signal of this one. Is this clear? Any confusion on this? Any doubt? I can invert it also, but this is an easier way to draw. Is it clear? Confusing?
Yes.
Okay.
Yes.
So now, because V1 is 0 here, this will be 0, right? No current will be flowing because there is no potential difference between. This is also grounded, this is also grounded. So only this arrow will come into picture. So arrow will come into picture, and this arrow 2 will be in parallel with this arrow 1. Sorry, this is arrow 2 and GM2. So this arrow 2, you see, it is coming in parallel with arrow 1 because this one terminal is grounded, one is connected to the V out. So the gain of this amplifier in this case is arrow 1 parallel arrow 2. Okay. Of course, this is also not very high gain because we know that arrow are not. If it is 4 kilo ohms, then it is just totally it is 2 kilo ohms like that. So yeah, so if it is also not a very high gain, but this is the gain of this amplifier. So of course my question is how to get high gain, but this is not exactly high gain. This technique was used to get high gain for technology which was older than 180 nanometer, but this was valid actually because with this it is possible if RO is like very high, maybe 40k 50k, so it was possible to get high gain with this technique, but no more. It is no more valid whenever we are discussing with technology which has a very less RO like that. Okay, so this is one thing. The other thing is, if what happens if instead of putting in saturation, if it goes in the linear region, yes, this kind of amplifier are also used. So if it is goes in the linear region, we know that this MOSFET will behave like a resistor, and the on resistance is given by this value, right? I hope you already have learned about this. So it's not the BGS minus VTH. So this is the expression. So then the gain will be Gm. What will be the gain expression? Minus Gm into
or
RO1 parallel R12, right? Agree? Yeah. Of course, in our initial circuit also, I think I don't know if we have included RO. So in the initial analysis also, yeah, we have come to here, right? So yeah, we have considered this part also. This one. Okay. So this is one kind of amplifier, right? So the next thing is the diode connected device. So if I connect the gate and the drain, the gate and the source. In this case also this is source, gate and the drain, PMOS, right? So if I short the gate and the drain, these are called diode connected device, right? These are called diode connected device, and we can try to find out its impedance also. We can try to find out this impedance. So this impedance will be basically the impedance looking inside here. So it will be the impedance looking in this. I should say that here like that. So so let's consider the impedance looking at this node, maybe Rx, Rx dash maybe. So basically, and the Ix dash is flowing inside there, right? So basically, my impedance looking at this point, if it is Rx, Rx will be nothing but this RO parallel this Rx dash. Agree? Am I going too fast or it's okay? I just need the feedback. Yeah. Hello? Am I going too fast?
It's
Or it's
okay.
fine? Huh? Is it too fast or it's fine?
Fine.
Fine, right? Okay, great. So this Ix, what is this Ix now then? Ix dash? What is this Ix dash? GMV1, right? GMV1, and V1, if you see V1 is here to here, so it is same as Vx because it is sorted, right? So it is same as GMVx. You can try to analyze yourself at home. It's quite simple, no big deal in that. So so the Rx dash is nothing but 1 Vx by Ix dash is equal to 1 by Gm. So basically, the finally, so this Rx dash, right? Rx dash. So my Rx happens to be RO parallel 1 by Gm, right? So if now generally this 1 by Gm is much smaller than this RO, so we can approximate it to 1 by Gm. So what the point is, if I have this die connected device, generally the impedance looking into here is 1 by Gm. Agreed? Hello?
Yes.
Yeah. Great. So yeah, this is.
why are we calling this diode connected device?
That's a good question. Yeah. So a diode connected device because let's I think. So basically, what happens is when we do this kind of this one. So when we do when we connect this one and try to, if we plot basically the this VD versus the ID. So this will always be in saturation region, right? Of course, it can come to cutoff if VD is very this one. So the behavior is like a diode basically. The behavior of this device, although it's following square law, the diode actually follows exponential behavior, but it will also have, like, as soon as whenever this VD is less than VTH, it will not be conducting anything, right? It will not be conducting. But as soon as this VD becomes more than VTH, then it will try to follow the square law, and it is always like it is always having a this square law behavior, like, are you getting me? Because it is always in saturation region, and because it's just a two terminal, right? It's a two terminal, 1 2, so that's why this is called diode connected. There is no other region. Are you getting my point? Hello? Yeah,
Yes.
because the behavior is like a diode. Like after a certain voltage, it just shoots up. Like, although it is square law, diode, in actual diode, it is exponential, but here it is yeah, because of the behavior, it's called diode connected. No other region in that. Yeah. Okay. So now again, if we try to analyze with this GMB also, you can try to analyze this one. So this will be the impedance looking into this node, again, will be Rx. I'll leave for you to do the analysis. Again, this RO parallel, it will be 1 by GM plus GMB, right? Because actually this 2 will get added. If you see here, it is again the VVS here, it is quite same as this one, right? So it is VBS is also minus V1 will come here, and here also this V1 will be, so it will become as minus, basically minus Vx. So V1 is minus Vx, and this VVS is also minus Vx. So if you see the impedance, so it is RO parallel 1 by GM plus GMB, so which is nothing but again GM plus GMB. So now if I try to implement an amplifier with a diode connected load, right? With a diode connected load, my gain will be again. So what should be my gain now? Can you tell me the expression of the gain of this amplifier with this knowledge? That this impedance looking into this node is GM plus GMB approximately. Yeah. What is the gain of this, or parallel RO2? So what is the gain of this amplifier? Can someone tell? Yes, please. Minus GM into GM of this GM of 1. So the RO also will come into picture. So RO1 parallel RO2 parallel 1 by GM2 plus GMB2. And because this will be larger than this GM, so it is approximately equal to minus GM1 by GM2 plus GMB2. Okay. Is this clear? Hello? Yeah. Okay then, so I think this is the conclusion. So I have made a summary of this one. So I think this is quite, I think everyone should remember this one. So if I have a simple this kind of this is minus GM RD, or more precisely it is minus GM RO parallel RD, right? So this is the expression for this one. And as we have seen, if GM RD is much larger than 1, it is approximately equal to minus RD by RS, and the output impedance looking into this kind of configuration is 1 plus GM plus GMB RO RS. So this product is coming, RO into RS product is coming, so this is important. And if we have diode connected device, the impedance looking into it is 1 by GM plus GMB, and whereas for normal device it is RO is equal to ROut is equal to RO. So I think these are very important point that we should remember, and these things will keep coming again and again, especially this part will be dealing again and again. So yeah, I think I have rushed through it little fast, time is not there, and maybe you can just read this portion of the book and get the things more clear. I have taken the materials, everything from the book itself.